Hi, I'm Shannon Silva.
I'm Dennis Lachov.
I'm Noah Tornell.
And I'm Alex Zirkle. This is our senior project pulse delay generator.
Our team developed the Pulse Delay Generator, or PDG. It is an open-source FPGA-based tool designed for researchers exploring hardware security and fault injection attacks.
The PDG takes in a trigger signal and applies a precise, user-defined delay to generate an accurate output pulse.
This delay can be down to the sub-nanosecond range.
The PDG is designed to be affordable, reliable, and fully customizable, providing competitive performance and more reliable features than commercial alternatives.
The PDG includes a graphical interface allowing easy configuration and control for users without FPGA or Python experience. We also implemented a fully automated pulse sequencing workflow for repeatable tests with manual intervention. The core logic and interface code are fully documented and structured for open source release. Our hardware ensures high signal integrity and supports integration with external clock sources through a custom PCB for improved accuracy and jitter reduction.
Getting a reliably externally clocked system to work, not just in simulation, but on a physical FPGA, pushed us to deeply understand physical routing and synchronization. Implementing sub-cycle delays required careful handling of FPGA primitives, adjusting the Vernier delay line, and tuning the time-to-digital converter architecture to meet timing. While working as a team, we encountered issues with coordination, communication, and collaboration. This was due to conflicting schedules, confusion, and the health needs of our teammates.
This project taught us the importance of thorough preparation and communication. Double-checking specifications and footprints before ordering components would have reduced time, budget, and delivery emissions. Defining project goals early on helped us stay focused and prioritize the right features to deliver a complete and fully functional system on time. Good collaboration was important for our project. It means supporting each other and working dynamically to account for each other's lives and capabilities.
The PDG is composed of 7 main modules, which are associated with either the computer or FPGA board. On the computer side, the control interface runs the user interface and manages communication with the FPGA. It sends configuration data such as target delay and pulse width, and receives measurement data back from the system. Inside the FPGA, the communication module handles data exchange with the control interface. It routes user-provided settings to the appropriate blocks and sends system measurements or status updates back to the UI. The clock interface accepts an optional 10 MHz external clock. If provided, it multiplies the external clock to 200 MHz and supplies it as the system clock. If no external clock is connected, the internal oscillator is used instead.
The asynchronous trigger detector handles external trigger signals that are not synchronized to the system clock. It uses a time-to-digital converter, or TDC, to precisely measure the offset between the rising edge of the trigger and the next clock edge. Next, the delay calculator receives the TDC result and target delay value. The system clock won't be able to perfectly align with the trigger because the trigger is asynchronous. To account for this, the delay calculator determines the necessary combination of coarse and fine delay needed to achieve the desired delay value. The delay generator implements the delay calculated by the delay calculator. It includes two components, a coarse delay counter that advances in 5 nanosecond steps, and a fine delay element that fills in sub-cycle remainder with picosecond resolution. Finally, the pulse generator activates the output signal after the calculated delay. It holds the output high for the programmed pulse duration and then shuts off, completing the timing sequence with nanosecond level accuracy.
Our graphical user interface is built in Jupyter Notebook. It includes a checkbox for enabling the external clock. When the box is selected, the system will attempt to use the external 10 MHz input instead of the internal oscillator. Below that are two input fields, one for the delay length and one for the pulse width. After entering the desired values, the Enter button can be pressed to configure the system and automatically arm it.
This is the physical system housed inside the enclosure. The main components include the FPGA chip, mounted on a development board, a separate debugging board for test access, and a custom PCB that handles signal routing and I/O.
We connected our PDG to power in our laptop for system validation, then configured the parameters via Jupyter Notebook. To measure PDG behavior, we used a 10 GHz oscilloscope connected to the output. Our oscilloscope also performs the function of a trigger signal via its arbitrary waveform generator.
While the PDG performs reliably for most fault injection and timing-sensitive applications, there are a few limitations to be aware of. The system exhibits picosecond level jitter on both delay and pulse, which is acceptable for many use cases, but may not meet ultra-precision requirements. The minimum achievable delay is 25 nanoseconds, and the shortest pulse width is 5 nanoseconds, which sets the lower bound for fine-grained control. Mechanically, the current PCB revision could benefit from added reinforcement, particularly for long-term lab use or repeated handling. Additionally, the external clock input is currently single-ended rather than differential, which may impact noise immunity in some environments.
The pulse delay generator brings together accessibility, precision, and flexibility in a compact open source platform. Many find the system accessible and easy to use.
We've achieved nanosecond level accuracy in both delay and pulse generation, supported by a high integrity hardware design and optional external clock input.
The entire system, from the FPGA core to the interface code, is fully documented and ready for open source release.
By combining practical usability with precise timing control, the PDG stands as a capable and affordable tool for researchers working in hardware security and fault injection.
Thank you for watching our Senior Capstone project video.